Sorting looks boring until you realize almost everything fast depends on it. Search, databases, recommendations, even the binary search from last time, they all assume the data is already in order. So the real question is, how do you sort a million things quickly, and why do the two best methods disagree about how? Today it's Quicksort versus Mergesort, the two sorts you'll be asked to explain in almost any interview. By the end you'll see exactly how each one works, why they're both n log n, and the surprising reason your phone secretly uses both. This is Logic Lab, where computer science becomes something you can see. Today, two clever ways to put a million things in order and when each one wins. First, why not the obvious way? The naive sort compares every item to every other, a loop inside a loop. That's O of n squared. For 100 items, 10,000 steps, fine. For a million items, a trillion steps. Your laptop would still be sorting tomorrow. We need something smarter, and the trick is the same one as last time: divide and conquer. Both of today's algorithms split the problem in half, solve each half, and combine. They just disagree about where the clever part lives, in the splitting or in the combining. That single choice changes everything about how they behave. Quicksort does the work up front in the split. Pick one element, call it the pivot. Now partition. Walk the array and shove everything smaller than the pivot to its left, everything larger to its right. After one pass, the pivot is sitting in its final, correct position, even though nothing else is sorted yet. Then you do the same thing to the left chunk and the right chunk. Pick a pivot, partition, recurse. Each level places more pivots, the chunks get smaller, and the whole thing falls into order. The combined step is nothing. Once the pieces are sorted in place, you're done. When the pivots split things roughly evenly, you get about log n levels, each doing n work to partition. So n times log n Quicksort is also in place. It shuffles within the same array, using almost no extra memory. That's why it's often the fastest in practice. Mergesort flips the strategy. The split is dumb, the combine is clever. Split the array in half. Split those halves. Keep splitting until every piece is a single element, and a single element is trivially already sorted. Now the real work: merging. Take two already sorted piles and zip them into one sorted pile. Compare the fronts, take the smaller, repeat. Merging two sorted lists is fast and foolproof. Merge pairs, then merge the merges, climbing back up until the whole array is one sorted list. Splitting gives log n levels. Each level merges a total of n elements. Again, n times log n, but notice, merging needs somewhere to put the combined list, so Mergesort uses extra memory, O of n scratch space. That cost buys it something valuable, as we'll see. Here's where they part ways, the worst case. Mergesort always splits exactly in half, so it's n log n guaranteed every time, no matter the input. Rock solid. Quicksort's speed depends on good pivots. Feed it already sorted data and naively pick the first element as pivot, and every partition peels off just one item, n levels instead of log n. That collapses Quicksort to O of n squared. It's nightmare case. The fix: choose the pivot randomly or from the median, making that disaster astronomically unlikely. One more difference that matters in the real world: stability. Mergesort is stable. Equal items keep their original order. Quicksort, as usually written, is not. When you sort a table by date, then by name, stability is what keeps the dates from scrambling. So which wins? Quicksort, usually fastest, in place, cache-friendly, but a risky worst case and not stable. Mergesort, guaranteed n log n and stable, but needs extra memory. There's no universal winner, there's a right tool for the constraints. Which is why real languages cheat and use both. Python's sort and Java's object sort use timsort, a hybrid that merges like Mergesort but exploits already ordered runs. Many Quicksort libraries fall back to a different method when recursion goes too deep, dodging the worst case. The pros don't pick one, they combine their strengths. Recap. Naive sorting is n squared and dies at scale. Divide and conquer gets us to n log in two ways. Quicksort partitions around a pivot fast and in place, but a bad worst case unless you randomize. Mergesort splits to single elements and merges, guaranteed n log n and stable at the cost of extra memory. Same speed class, opposite trade-offs. We just solved a problem by breaking it into halves and combining the answers. But what about problems where the pieces overlap, where you'd solve the exact same subproblem 1,000 times? There's a trick for that and it feels like cheating. That's next on Logic Lab. See you there.